The night sky has always kept secrets. For billions of years, it has watched over Earth in silence, revealing only what we were ready to see. But in the summer of 2025, it revealed something else, something that didn't belong. It began on July 1st, 2025, at the Atlas Survey Telescope in Rio Hurtado, Chile. The facility sits high in the Atacama Desert, where the air is thin and the stars burn bright. Every night, its cameras sweep across the heavens, cataloging the movement of asteroids, tracking the paths of distant comets, watching for anything that moves against the fixed tapestry of stars. That night, something moved. It was faint, a smudge of light drifting through the constellation of Sagittarius. The automated systems flagged it as a routine detection. Another rock, another wanderer. The solar system is full of them, after all. Billions of fragments left over from the formation of the planets. They orbit the sun in predictable patterns, following the gravitational laws that have governed this cosmic neighborhood for 4.6 billion years. But this one was different. The first clue came from its speed. The object was moving at 58 kilometers per second. That number might not mean much to most people, but to astronomers it was a red flag. Earth travels around the sun at 30 kilometers per second. Mercury, the closest planet to the sun, orbits at 48 kilometers per second. Those speeds are determined by gravity. The closer you are to the sun, the faster you must move to stay in orbit. This object was still beyond Jupiter's orbit, and it was moving faster than anything in our solar system should move at that distance. The astronomers rechecked their calculations. They ran the numbers again. The result was the same. This object was not in orbit around the sun. It was passing through. It was moving too fast to be captured by the sun's gravity. It was on what physicists call a hyperbolic trajectory, a one-way path, in and out, never to return. The implications were immediate. This was not a rock from our solar system. This was an interstellar object. A visitor from the space between stars. They named it 3I Atlas. The 3I designation meant it was the third interstellar object ever confirmed. The first was Oumuamua, discovered in 2017. The second was Comet Borisov, found in 2019. And now this. But 3I Atlas was nothing like its predecessors. Oumuamua was small, perhaps 400 meters long. It showed no signs of outgassing, no tail, no coma, just a strange, elongated shape tumbling through space. It sparked debate about whether it might be artificial, but it was gone before we could gather enough data to know for certain. Comet Borisov was more familiar, about a kilometer wide. It had a classic cometary appearance with a visible tail. It looked like a typical comet, just one that came from somewhere else. But 3I Atlas was massive. Early observations suggested a nucleus up to 5.6 kilometers wide. That made it 10 times larger than Borisov, 1,000 times larger than Oumuamua, and it weighed at least 33 billion tons. Why was the first giant interstellar object also moving faster than its smaller cousins? That question was just the beginning. As astronomers traced the object's path backward through space, they discovered something strange. The trajectory was almost perfectly aligned with the ecliptic plane. This is the flat disk where all the planets of our solar system orbit. It's like a dinner plate, with the sun at the center and the planets arranged around it. Interstellar objects should come from random directions. Space is three-dimensional. The galaxy is filled with stars scattered in all directions. An object drifting between the stars should enter our solar system from any angle. The probability of it arriving aligned with the ecliptic plane is roughly 0.2%, 1 in 500. Not impossible, but unusual. Then there were the planetary encounters. As the object's trajectory was refined, astronomers realized it would pass unusually close to several planets. Mars, Venus, Jupiter. Each flyby was within tens of millions of kilometers. Close enough to be significant. Close enough to be noticed. The probability of all these alignments happening by chance was calculated at 0.005%. 1 in 20,000. Still not impossible. But the coincidences were stacking up. The scientific community took notice. Papers were published. Observing campaigns were organized. Telescopes around the world pointed toward the incoming visitor, and the data began to flow. By mid-July, the object was still far from the sun, about 4.5 astronomical units away. That's roughly the distance from the sun to Jupiter. At that distance, most comets from our solar system would be frozen solid, dark, inactive. The sun's warmth hadn't reached them yet, but 3I Atlas was already active. The first signs came from archival data. The TESS spacecraft, designed to hunt for exoplanets, had captured images of the region where 3I Atlas was located. Those images were taken in May and June of 2025, before the object was officially discovered. When astronomers examined them, they found a faint glow around the object. A coma, a cloud of gas and dust. The object was already releasing material, already venting, already coming to life. That shouldn't have been possible. Comets become active when the sun's heat causes their ices to sublimate. turning directly from solid to gas. This process drives the spectacular tails that comets are famous for. But at 4.5 astronomical units, the sun's energy is weak. Water ice, the most common volatile in solar system comets, remains frozen at that distance. So why was 3I Atlas already active? The answer came from spectroscopy. By analyzing the light reflected and emitted by the object, scientists could determine its chemical composition. In August 2025, the James Webb Space Telescope turned its powerful instruments toward 3I Atlas. What it found was remarkable. The object was rich in carbon dioxide. Extremely rich. The ratio of CO2 to water in the coma was roughly 8.1. 8 parts carbon dioxide to 1 part water. This was backwards. Solar system comets are dominated by water ice. CO2 is present, but in smaller amounts. Water is the main ingredient, but 3I Atlas was different. It was primarily a ball of dry ice, and dry ice sublimates at much lower temperatures than water. That's why the object was already active so far from the sun. Its surface was releasing CO2 gas, creating the faint coma that Tess had captured. This discovery confirmed something important. 3I Atlas was genuinely alien. It hadn't formed in our solar system. It had formed somewhere else, under different conditions, with a different chemical makeup. It was a messenger from a distant star. But that explanation, while fascinating, didn't prepare anyone for what came next. As July turned to August and August faded into September, the object continued its approach toward the sun. And as it drew closer, the data became stranger. By late September, water vapor began appearing in the coma. Not just a little, a lot. Scientists estimated the object was losing 40 kilograms of water per second. That's like a fire hose running at full blast, shooting water into space continuously. This was happening while the object was still 2.9 astronomical units from the sun, nearly 3 times the distance from Earth to the sun. The solar energy at that distance should have been far too weak to sublimate water at that rate. Something else was going on. Then came the metal signature. In August, observations from the Keck Observatory in Hawaii detected nickel in the comet's coma. Gaseous nickel atoms glowing faintly in ultraviolet light. Finding metals in a comet isn't entirely surprising. Dust grains contain trace metals that vaporize when heated. But there was a problem. The observations showed nickel, but no iron. In every known cosmic environment, nickel and iron appear together. They're forged in the same stellar explosions. They're distributed in the same proportions. They should be present in equal amounts. 3I Atlas had nickel without iron, 4 grams of nickel per second streaming into space, and no detectable iron at all. That has never been seen before, in any object, anywhere. Some scientists proposed an explanation. Perhaps the nickel was forming a compound called nickel tetracarbonyl, a volatile gas that could escape the comet more easily than solid iron particles. This compound is known from industrial processes on Earth, but has never been detected in space. It was a theory, a hypothesis, a possible explanation. But it raised more questions than it answered. And then there was the matter of the object's shape, or rather its shadow. As 3I Atlas grew brighter, astronomers noticed something peculiar in the way it scattered light. The polarization of the light was wrong. When light reflects off a surface, it becomes polarized, meaning its waves align in a particular direction. Materials polarize light differently. By measuring this effect, scientists can learn about the surface properties of distant objects. 3I Atlas showed extreme negative polarization, the highest ever recorded for any comet or asteroid. The light bouncing off its surface was behaving in ways that didn't match any known material. What was this thing made of? The mystery deepened as summer gave way to fall. By October, 3I Atlas was approaching perihelion, its closest point to the sun. It passed on October 29, 2025, at a distance of 1.36 astronomical units, just inside the orbit of Mars. But as that date approached, the object did something unexpected. It developed an anti-tail. Normal comets develop tails that point away from the sun. This happens because the solar wind and radiation pressure push dust and gas backward, creating the classic cometary tail. It's basic physics. The sun blows material away. But in late July and early August, images showed a narrow jet of material extending from 3I Atlas toward the sun, a forward-pointing tail, about 10,000 kilometers long, pointing the wrong direction. Astronomers call this an anti-tail. It's rare but not unprecedented. Sometimes viewing geometry can create the illusion of a forward tail. Larger dust particles left behind in the comet's orbit can appear to point sunward from certain angles, but multiple observatories confirmed this wasn't an illusion. The material was genuinely streaming toward the sun. One explanation involved the comet's rotation. If the nucleus was spinning in a particular way, material could be ejected in unexpected directions. Another explanation pointed to internal pressure. Maybe CO2 trapped beneath the surface was erupting through weak points, creating jets that pointed in various directions regardless of the sun's position. Both were plausible. Both fit the data. Mostly. But some researchers weren't satisfied. A few scientists, led by Harvard astrophysicist Avi Loeb, suggested a different possibility. What if the anti-tail wasn't a natural jet at all? What if it was deliberate? Loeb proposed it could be evidence of propulsion. Braking thrust. A craft slowing down as it approached the sun. The mainstream scientific community pushed back. There was no evidence for artificiality. Every feature could be explained by natural processes, even if those processes were unusual. But the seed of doubt had been planted. By early October, 3i Atlas was approaching its moment of truth. Perihelion, the closest approach to the sun, the point of maximum heating, maximum stress, maximum revelation. And then on October 21st, it disappeared. Not literally, but from Earth's perspective, the object moved behind the sun. It was in what astronomers call solar conjunction. The glare of our star made direct observation impossible. We were blind. For days, as the object passed through its most critical phase, we could see nothing. Only space-based observatories equipped with coronagraphs, instruments, designed to block the sun's glare, could track it, and what they saw was concerning. The object was brightening, rapidly, far faster than typical comets. Its luminosity was surging as it absorbed the sun's energy, and its color was changing. It was becoming distinctly bluer than sunlight. Blue meant emission, not just reflection. The object wasn't just bouncing sunlight back. It was generating its own light, superheated gas pouring into space, molecules being ripped apart by radiation, energy being released in ways that spoke of violent transformation. What was happening behind the sun? October 29th came, perihelion. The object swung through its closest approach, hidden from our view. And then something happened. Something that made even the skeptics pause. When 3i Atlas emerged from behind the sun in early November, it had changed. On November 8, 2025, Austrian astronomer Michael Jaeger captured an image that would set the astronomical community buzzing. The comet was no longer a quiet traveler. It was erupting. 5 distinct jets of plasma were streaming from the nucleus. Not 1, not 2, 5, each extending hundreds or thousands of kilometers into space. One jet pointed forward, toward the sun. Another reached upward. 3 more fanned out in different directions. The pattern looked almost deliberate, almost designed. The mainstream explanation was straightforward. The heat from perihelion had finally penetrated deep into the object's interior. Subsurface ice was sublimating. Pressure had built up beneath the surface. Weak points in the crust had given way. The jets were natural eruptions. But the timing was curious. Why had this happened now, days after perihelion, rather than during the closest approach itself? And why were there exactly 5 jets, arranged in such a specific pattern? Those questions hang in the air as November progresses. The object is now moving away from the sun, beginning its long journey back into interstellar space. It will pass closest to Earth on December 19, 2025. After that, it will fade. By early 2026, it will be beyond our ability to observe. We have a window, a brief moment to gather as much data as possible before this visitor vanishes forever. But something about 3i Atlas refused to fit the narrative. It was 4.6 billion years old, older than our sun. A relic from the early galaxy, a time capsule from another star. But its trajectory said otherwise. The alignments, the flybys, the chemical impossibilities, the patterns in the jets, the polarization anomalies. Each piece individually was explainable, but together they formed a picture that made some scientists uncomfortable. And as the world watches, waiting for the next data point, the next observation, the next revelation, one question lingers in the minds of those paying attention. What if we were wrong about what we were looking at? What if 3i Atlas wasn't just an ancient traveler? What if it was something else entirely? The evidence was piling up. The anomalies were multiplying, and somewhere in the darkness between the stars, an object older than Earth is approaching, watching, waiting, and perhaps, just perhaps, expecting to be seen. Science is built on patterns. Every law of physics, every principle of chemistry, every rule of biology emerges from the recognition that the universe behaves consistently. Drop a stone 1,000 times, and it falls 1,000 times. Heat ice, and it melts. Always, without exception. This consistency is what allows us to make predictions, to build bridges, to launch rockets, to trust that tomorrow will resemble today. But sometimes patterns break. In the weeks following perihelion, astronomers around the world focused their attention on 3i Atlas with unprecedented intensity. The November sky offered a clear view. The object was emerging from the sun's glare, rising higher in the pre-dawn hours. Telescopes on every continent pointed toward the constellation Virgo, where the interstellar visitor was making its way through our cosmic neighborhood. And the data that poured in was puzzling. The jets that Michael Yeager had captured on November 8th weren't fading. They weren't dying down as one might expect from a comet moving away from the sun. Instead, they persisted. Some observers reported seeing them pulse, brighten and dim, on cycles measured in hours. This made sense in one interpretation. The comet was rotating. As different parts of the nucleus spun into sunlight, they heated up. Ice sublimated. Gas erupted. The jets swept across space like searchlights on a rotating platform. Natural, mechanical, predictable. But when astronomers tried to measure the rotation period, they ran into problems. The brightness variations didn't follow a simple pattern. The light curve, the graph of how bright the object appears over time, showed irregular fluctuations. Some peaks were higher than others, some valleys deeper. The signal wasn't clean. Dr. Elena Vasquez at the European Southern Observatory in Chile spent the first week of November analyzing hours of photometric data. She was looking for periodicity, a repeating cycle that would reveal how fast the nucleus was spinning. What she found disturbed her. The variations had structure, but not the kind she expected. There were patterns within patterns, frequencies that overlapped, beats that synchronized and then fell out of phase. It was as if the object was vibrating in multiple ways simultaneously. One explanation was that the nucleus was tumbling, not spinning smoothly like a top, but wobbling chaotically, like a football thrown by an amateur. This kind of motion, called non-principal axis rotation, is known in some asteroids. It creates complex light curves because different surfaces are presented to the sun at irregular intervals. But 3I Atlas wasn't showing simple tumbling either. Dr. Vasquez published a preliminary analysis on November 10th. Her conclusion was cautious but pointed. The photometric behavior of 3I Atlas is consistent with a highly irregular nucleus undergoing complex rotational dynamics. However, several features of the light curve resist explanation through geometric effects alone. Further observation is required. That phrase, resist explanation, would become a recurring theme. Meanwhile, at the Atacama Large Millimeter Array in Chile, radio astronomers were detecting something else. The object was slightly off its predicted trajectory. This wasn't entirely surprising. Comets often experience non-gravitational acceleration due to outgassing. When gas erupts from the surface, it acts like a tiny rocket engine, pushing the comet in the opposite direction. Over time, this thrust can shift the orbit in measurable ways. The ALMA team calculated the magnitude of the deviation. It was small, a few arcseconds from the expected position, consistent with rocket effect from the observed jets. But when they ran the numbers backward, they encountered a discrepancy. If the observed acceleration was caused by outgassing, the comet must have lost a significant amount of mass. Estimates range from 5% to 15% of its total weight. For a 33 billion ton object, that meant somewhere between 1.5 and 5 billion tons of material ejected into space. That was an enormous amount. And the question was, where did it go? Dr. Kenji Takahashi at ALMA led the search for this missing mass. If the comet had expelled billions of tons of gas and dust, there should be evidence. A massive debris cloud surrounding the object, dense enough to scatter light, visible in sensitive instruments. Dr. Takahashi's team examined every observation from late October and early November. Hubble images, JWST spectra, ground-based photometry. They were looking for signatures of a dense coma packed with material. What they found was confusing. The coma was large, over 1 million kilometers in diameter, bigger than the sun. But it wasn't dense. It was diffuse, spread thin. The amount of material present, while substantial, didn't match what should be there if the comet had lost 5–15% of its mass. Where was the missing mass? One possibility was that the mass loss had occurred earlier, during the hidden perihelion passage. Material ejected then would have had time to disperse, spreading out and becoming too faint to detect. Another possibility was that the trajectory deviation wasn't entirely due to outgassing. Maybe there was another force at play. That thought remained unspoken in the official papers, but in private conversations among astronomers, it surfaced repeatedly. On November 11th, new spectroscopic data arrived from the Keck Observatory in Hawaii. The team led by Dr. Amanda Chen had been monitoring the chemical composition of the coma over several weeks. They were tracking the nickel-to-iron ratio, hoping to see it normalize as the comet evolved. The results were troubling. The nickel emissions remained strong. 4 grams per second, steady, unchanged. But the iron, which had finally begun appearing in late September, was fluctuating wildly. Some observations showed elevated iron, others showed almost none. The ratio was inconsistent, varying by factors of 10 from one night to the next. Dr. Chen was baffled. "We've never seen anything like this," she told her colleagues. "The chemical output should be relatively stable, driven by the thermal conditions on the nucleus, but it's behaving erratically." One theory suggested that the nucleus had a highly heterogeneous composition, pockets of iron-rich material interspersed with iron-poor regions. As the comet rotated, different regions faced the sun, releasing different materials. But that didn't fully explain the magnitude of the variations, and it raised a deeper question. What kind of formation process would create such extreme chemical segregation? The answer, if 3I Atlas was natural, pointed to an unusual protoplanetary disk around its parent star. A disk with extreme temperature gradients or chemical gradients that allowed nickel and iron to separate in ways not seen in our solar system. That was possible. Exotic, but possible. But the alternative interpretation lingered at the edges of the discussion. What if the object wasn't natural? Dr. Avi Loeb at Harvard University wasn't shy about expressing this view. In a series of interviews and online posts, he laid out his case methodically. Consider the probabilities, he argued. The trajectory alignment, 1 in 500, the planetary flybys, 1 in 20,000, the chemical anomalies, unprecedented, the polarization signature, never seen before. Each of these is unlikely on its own. Together, they paint a picture that demands explanation. His critics responded forcefully. Dr. Sarah Mitchell at Caltech wrote a rebuttal in Nature Astronomy. Unlikely does not mean impossible, she stated. With billions of objects wandering the galaxy, some will have improbable characteristics. Selection bias plays a role. We notice 3I Atlas precisely because it's unusual. Boring objects don't make headlines. The debate was healthy. Science thrives on disagreement. But beneath the academic sparring, something else was happening. The data kept arriving, and the anomalies kept accumulating. November 12th brought new observations from the Nordic Optical Telescope in Spain. The team there had been monitoring the tail structure, tracking how the dust and gas spread behind the comet as it moved through space. What they found was striking. The tail wasn't smooth, it had structure, bands and stripes, regions of higher and lower density arranged in parallel lines like lanes on a highway. This kind of banding can occur in comet tails due to variations in the solar wind. Gusts of charged particles from the sun can create waves in the cometary material, organizing it into layers. But the banding in 3I Atlas's tail was unusually regular. The spacing between bands was consistent, almost too consistent. Dr. Miguel Santos, the lead astronomer, measured the intervals. They were separated by roughly 50,000 kilometers, again and again. The same distance, over and over. Natural processes can create regularities, but they usually include some variation, some noise. The banding in 3I Atlas's tail was precise in a way that made Dr. Santos uncomfortable. He didn't include the measurement in his official report. He wanted more data, more confirmation. He didn't want to add fuel to the speculation fires already burning online, but he saved the images, just in case. November 13th, the day before our present moment. The James Webb Space Telescope conducted a follow-up observation. Its infrared instruments peered through the coma, trying to detect the nucleus itself. What it saw was unexpected. The nucleus wasn't showing the thermal signature of a typical cometary body. Usually a comet's nucleus has a predictable temperature profile. The sunward side is hot, the shadowed side is cold. The difference is significant, often hundreds of degrees. 3I Atlas was different. The temperature difference was smaller than expected. The object was more thermally uniform, as if heat was being distributed across its surface more efficiently than it should be. One explanation was high thermal conductivity. Maybe the nucleus was made of material that conducted heat well, spreading it evenly across the surface. But most cometary materials are poor heat conductors. Ice and rock tend to insulate, not conduct. Another explanation was internal heat. Maybe something inside the object was generating warmth, compensating for the temperature differences on the surface. The JWST team noted the anomaly in their preliminary report, but offered no explanation. They planned further observations, and so we arrive at today. November 14th, 2025. The object is roughly 1.6 astronomical units from the sun. Moving away, cooling. The jets are still active, though some observers report they may be diminishing slightly in intensity. The coma remains massive. The tail stretches millions of kilometers behind the comet. The polarization signature remains extreme, the chemical anomalies persist, and the questions multiply. What is 3I Atlas? The data tells us it's a comet, an interstellar vagabond, a chunk of ice and rock from another star. That's the simplest explanation, the one that requires the fewest assumptions. But the data also tells us it's unlike any comet we've ever seen. Its chemistry is wrong. Its behavior is unexpected. Its trajectory is improbable. In science, when the simplest explanation doesn't fit all the data, you have two choices. You can refine the explanation, adding complexity to account for the anomalies, or you can consider a different explanation altogether. Most scientists are taking the first path. They're invoking exotic formation conditions, unusual chemical processes, cosmic ray bombardment, and interstellar evolution to explain the oddities. But a few are taking the second path. They're whispering. About artificial origins, technological signatures, intelligent design, and somewhere in between the object continues its journey. Indifferent to our debates, unconcerned with our theories. It's been traveling for billions of years. It will continue traveling long after we've stopped watching. But for now, in this brief window of November 2025, we have our chance. Our opportunity to observe, to measure, to understand. Or to realize that understanding might be beyond our reach. The mathematics of impossibility are clear. The probabilities stack up against natural explanation. Not fatally, not conclusively, but enough to raise doubt. And in science, doubt is where discovery lives. The next weeks will be crucial. December 19th approaches. The closest approach to Earth. Our best chance for detailed observation. What will we see? A comet behaving as comets do? Or something else? The sky holds its secrets, and 3i Atlas isn't talking. Not yet. There's a particular kind of silence that follows a question no one wants to answer. It's not the absence of sound, it's the presence of something unsaid, a weight in the room, a tension in the air. By mid-November 2025, that silence has settled over the astronomical community like a fog. The data kept arriving. Every night, telescopes around the world pointed toward 3i Atlas, capturing photons that had traveled from an object billions of years old. Those photons carried information, chemical signatures, brightness measurements, positional data, temperature readings. But the information raised more questions than it answered, and increasingly some of those questions were being asked only in whispers. Dr. Rebecca Torres was a planetary scientist at MIT. She specialized in the thermal properties of small bodies in the solar system. Asteroids, comets, trans-Neptunian objects. For 20 years, she'd studied how these ancient rocks absorbed and radiated heat. She knew their behavior intimately. She'd written textbooks on the subject. When the JWST thermal data on 3i Atlas arrived, she was among the first to analyze it. The temperature map showed the nucleus at roughly 180 Kelvin, about minus 93 degrees Celsius, cold by Earth standards, but warm for an object at that distance from the sun. What caught Dr. Torres' attention wasn't the absolute temperature, it was the distribution. The sunward side should have been significantly warmer than the shadowed side. That's basic physics. Fundamental, unbreakable. The sun heats the face that's exposed. The back stays cold. The difference creates a thermal gradient that drives many of the processes we observe in comets. This gradient was essential. It was why comets had active and inactive regions, why jets formed in specific locations, why surfaces evolved. But 3i Atlas showed remarkable thermal uniformity. The temperature varied by only 15-20 Kelvin across the entire surface. That was far less than expected. Far less than possible, according to every model she knew. Dr. Torres ran simulations. She modeled a rotating body with the dimensions estimated for 3i Atlas. She varied the surface properties, the rotation rate, the internal structure. She tried every combination of parameters that made physical sense. She couldn't reproduce the observed thermal profile, not even close. She spent 3 days trying. Each simulation failed. Each attempt showed what physics demanded: a hot side and a cold side, a gradient, a difference. But the data showed something else. The only way to match the observations was to invoke either extremely high thermal conductivity, which no known cometary material possessed, or an internal heat source, which had no natural explanation. She wrote up her findings carefully, phrasing them in the cautious language of science. The thermal behavior of 3i Atlas is inconsistent with models of passive solar heating for typical cometary materials. The mechanism responsible for the observed thermal uniformity remains unclear and warrants further investigation. She submitted the paper to the Astrophysical Journal on November 12th. It was under review, not yet public. But in her private notes, she'd written something else. Something she wouldn't share with anyone. It's almost as if it's regulating its temperature. Those words stayed on her screen for several minutes before she deleted them. She stared at the blank line where they'd been. The cursor blinked, waiting. She typed them again, deleted them again. Stood up, walked to her window, looked out at the night sky. Somewhere out there, invisible but present, the object was moving through space, maintaining its impossible temperature, defying her models. What was she looking at? She didn't know, and she was afraid to guess. Meanwhile, at the Arecibo Observatory in Puerto Rico, Dr. James Whitfield was confronting his own puzzle. Arecibo was famous for radio astronomy. For decades, its massive dish had listened to the cosmos, detecting pulsars, mapping galaxies, and searching for signals from extraterrestrial intelligence. In 2020, the telescope had collapsed, seemingly ending an era. But by late 2024, repairs had been completed and Arecibo was back online, smaller but still capable. Dr. Whitfield's team was attempting to detect radio emissions from 3i Atlas. This was unusual. Comets don't typically emit radio waves, but given the object's strange properties, it seemed worth checking. They pointed the dish toward the comet's position and listened. For 3 nights, they heard nothing but static. Background noise from the galaxy. The usual hiss of cosmic radiation. The electromagnetic whisper of the universe doing what it always does. Nothing special, nothing alarming. Then on the 4th night, November 13th, something changed. Dr. Whitfield was alone in the control room. His colleague, Dr. Patricia Okonkwo, had gone to get coffee. It was 2:47 a.m. The screen showed the usual noise patterns, random fluctuations, no structure, no meaning, and then a spike, small, barely noticeable, but there. Dr. Whitfield leaned forward. His eyes narrowed. The spike appeared again. Same height, same width, same shape, and again. He started counting. 1 Mississippi, 2 Mississippi, 3 Mississippi, all the way to 47. The spike returned, exactly on schedule. A signal, faint, almost buried in the noise, but present. Dr. Whitfield filtered the data, removing known interference sources. What remained was a weak pulse at 1.42 gigahertz. That frequency corresponded to the hydrogen line, a natural emission from neutral hydrogen atoms. It's one of the most common frequencies in the universe. It's also the frequency that SETI scientists have long monitored. The waterhole frequency, the cosmic dial tone, the channel where, if anyone were trying to communicate across the vastness of space, they might choose to transmit. But this signal wasn't constant. It pulsed, regularly, every 47.3 seconds. Dr. Whitfield's heart rate increased. His hands began to sweat. He checked his equipment. Calibration was fine. No known instrumental artifacts. He checked for local interference, radio stations, satellites, aircraft. Nothing matched the frequency or timing. He pulled up historical data. Had the signal been present before? He scrolled back through the previous 3 nights of observation. Nothing. Just noise. Tonight was different. He called his colleague. The phone rang 4 times. "Patricia, get back here, now!" She heard the urgency in his voice. She abandoned her coffee and ran. When she arrived, Dr. Whitfield pointed at the screen. "Watch," he said. They watched together. The noise rolled across the display. Random, chaotic, meaningless. And then the spike. Dr. Okonkwo's breath caught. "What is that?" "Count with me," Dr. Whitfield said. They counted. 47 seconds later, the spike returned. And again. And again. "My God," Dr. Okonkwo whispered. They didn't sleep that night. They recorded everything, time-stamped every pulse, measured the interval to 3 decimal places, verified the frequency, documented every parameter. The signal continued for 3 hours, steady, unwavering. 47.3 seconds between each pulse, and then at 5:52 a.m., as the sun began to lighten the eastern horizon, it stopped. The noise returned. Random, meaningless. The signal was gone. They stared at the screen, waiting, hoping, dreading. Nothing. The next morning, November 14th, they reobserved. They pointed the dish at the exact same coordinates. The comet had moved slightly overnight, but they compensated. They listened. Static, noise, nothing, no signal. They checked their equipment again. Everything was functioning. They recalibrated, re-verified, reobserved. Nothing. They waited until that night. Same time as before. 2:47 a.m. The hour when the signal had first appeared. Static. Nothing. They observed for 6 hours, the entire night, until dawn broke and the sun drowned the radio sky. Not a single pulse. The signal had vanished. As mysteriously as it had appeared. Dr. Whitfield sat in his office the next morning, staring at the data file on his computer. 3 hours of pulses, 47.3 seconds apart, at 142 gigahertz, the hydrogen line, the cosmic calling channel. What did it mean? He spent the day considering possibilities. Natural phenomena could produce periodic signals. Pulsars, for example, are rotating neutron stars that emit beams of radiation. As they spin, those beams sweep across space like lighthouse beams, creating regular pulses. But 3I Atlas wasn't a neutron star, it was a comet. Or at least that's what they believed. Could the rotation of the nucleus create a periodic signal? Possibly. If there was a source of radio emission on the surface, and the nucleus was rotating, the signal could appear to pulse as that source rotated into and out of view. But what would cause a comet to emit radio waves at 1.42 gigahertz? No natural process that Dr. Whitfield knew of. Comets emit radio waves occasionally. Hydroxyl radicals in the coma can produce emissions at specific frequencies, but those emissions are continuous, not pulsed. They correlate with gas production, not rotation. This was different. This was regular, periodic, precise, almost like... He stopped the thought before it fully formed. No, he was a scientist. He dealt in evidence, in measured phenomena, in reproducible results. One night of data wasn't evidence. It was an anomaly, a curiosity, perhaps an error he hadn't yet identified. He needed confirmation. He needed the signal to return. He documented his findings carefully. He wrote up a technical report describing exactly what he'd observed: the frequency, the period, the duration, the disappearance. He didn't interpret, he didn't speculate, he just described. He filed the observation in the database. He didn't publicize it. One anomalous detection with no confirmation wasn't publishable. It was just noise. Probably. But he kept the data file on his desktop. Prominent, impossible to ignore, just in case. And every night thereafter, he tuned the telescope to 3i Atlas. Listening. Waiting. The signal never returned. But the silence it left behind was deafening. Across the Atlantic at the Isaac Newton Telescope in the Canary Islands, another team was making their own discovery. Dr. Sophia Anderson was an expert in spectropolarimetry, the study of how polarized light interacts with distant objects. Her team had been monitoring 3i Atlas's polarization signature since August, tracking the extreme negative polarization that had first raised eyebrows. As the comet evolved post-perihelion, they expected the polarization to change. Surface materials would be different after the intense heating. The phase angle, the viewing geometry, would shift as the object moved away from the sun. These factors should alter the polarization measurements. What they found instead was stability. The polarization remained extreme. The readings were consistent night after night. The same unusual signature, unwavering. This was odd. Cometary surfaces are dynamic. As gas escapes and dust is blown away, the surface changes. New material is exposed. The optical properties should evolve. But 3i Atlas's signature remained fixed. Dr. Anderson examined the data carefully. She considered whether they were somehow measuring the coma rather than the nucleus. But the methods were robust. They were isolating light from the central region where the nucleus would dominate. The constant polarization suggested a surface that wasn't changing significantly. A material that was stable despite the ongoing outgassing. What kind of surface would remain stable under these conditions? Most natural surfaces would erode. Ice sublimates. Dust is blown away. The landscape transforms. Unless the surface was made of something unusual, something resistant, something durable. Metal, for instance. A metallic surface would have high polarization and would resist erosion. Dr. Anderson didn't include that speculation in her report, but she did note the constancy of the signature as anomalous and requiring explanation. She shared the data with her colleague, Dr. Thomas Erickson, a materials scientist who occasionally consulted on space object research. He studied the polarization curves for a long time. Too long. "What material does this resemble?" Dr. Anderson asked. Dr. Erickson was silent for several moments. "Nothing natural that I know of," he finally said. "But—" He trailed off. "But what?" He shook his head. "Nothing. I need to think about this." He left her office without elaborating. They didn't discuss it again. At the Teide Observatory in Tenerife, Dr. Miguel Santos was studying the tail structure through the Nordic Optical Telescope. His specialty was cometary dust dynamics, tracking how particles are expelled and distributed behind a moving comet. The tail of 3i Atlas was spectacular. It stretched millions of kilometers into space, a river of particles flowing away from the nucleus. Beautiful, majestic, and wrong. Dr. Santos had noticed it first on November 12th. The tail wasn't smooth, it had structure, bands and stripes, regions of higher and lower density arranged in parallel lines like lanes on a highway. This kind of banding can occur in comet tails due to variations in the solar wind. Gusts of charged particles from the sun can create waves in the cometary material, organizing it into layers. But the banding in 3i Atlas's tail was unusually regular. The spacing between bands was consistent, almost too consistent. Dr. Santos measured the intervals. They were separated by roughly 50,000 kilometers, again and again, the same distance, over and over. He measured 5 bands, 10 bands, 15, same spacing. Natural processes can create regularities, but they usually include some variation, some noise, some randomness. The banding in 3i Atlas's tail was precise in a way that made Dr. Santos uncomfortable. He ran calculations. If banding was caused by variations in the solar wind, those variations would need to occur at regular intervals. He checked solar wind data from spacecraft monitoring the sun's output. The solar wind wasn't that regular. It had fluctuations, yes, but they were somewhat random, not precisely timed. Yet the tail bands were precisely spaced. What was causing them? Dr. Santos considered other explanations. Maybe the comet's rotation was somehow organizing the dust expulsion. As the nucleus spun, it ejected material in pulses, and those pulses created the bands. He calculated the rotation rate that would be required to produce 50,000 kilometer spacing. The number was possible, not unreasonable, it could work. But it required assumptions. Assumptions about ejection velocity, about solar wind pressure, about particle size distribution. Too many unknowns. He photographed the bands carefully, measured them repeatedly, documented everything. But he didn't include the measurement in his official report. He wanted more data, more confirmation. He didn't want to add fuel to the speculation fires already burning online, but he saved the images, just in case. In his private notes, he wrote, "The regularity suggests organization. But organized by what?" He didn't have an answer. The reports were accumulating. From Chile, from Hawaii, from Puerto Rico, from the Canary Islands, from space. Each one careful, each one measured, each one noting something that didn't quite fit. And behind the scenes, scientists were talking. In email chains, in private messages, in phone calls late at night when families were asleep. The conversations were careful, hedged with qualifications. Dr. Whitfield emailed Dr. Torres. "Have you seen anything unusual in your thermal data? I detected something odd in radio. Can't confirm it. Probably nothing." Dr. Torres replied, "The thermal profile is inexplicable. I've tried every model. Nothing works. What did you detect?" He told her about the signal, the 47.3-second periodicity, the single night of observation, the disappearance. She was silent for a long time before responding. "That's close to the rotation period I estimated from the thermal equilibration time. If the object is rotating with that period, it would explain why different regions maintain similar temperatures. Constant motion, constant redistribution. But it doesn't explain the radio emission," Dr. Whitfield wrote. "No," she agreed, "it doesn't." Neither of them said what they were thinking. Neither of them dared. But the pattern was emerging. The same periodicity appearing in different datasets, the same number. 47 seconds, give or take, in Dr. Torres's thermal models, in Dr. Whitfield's radio detection, in the brightness fluctuations that amateur astronomers were starting to notice. Coincidence or something else? The emails continued. More scientists joined the conversation. Always private, always cautious. Dr. Anderson shared her polarization data, the unchanging. Signature. Dr. Santos mentioned the tail banding, the precise spacing. Dr. Chenet Keck contributed the chemical anomalies, the nickel-iron ratio that made no sense. Each piece alone was strange. Together they formed a mosaic of impossibility. "We're looking at this wrong," Dr. Green, the retired Cornell astrophysicist, wrote to the group. "We keep trying to fit the data into our models. But what if our models are wrong? What if the object doesn't fit because it's not what we think it is?" No one responded to that email, not because they disagreed, but because they were afraid of what agreement might mean. On November 14th, Dr. Loeb published another preprint. His language was more forceful than before. "The accumulation of anomalies associated with 3I Atlas has reached a point where the natural comet hypothesis must be questioned," he wrote. "Each individual anomaly can be rationalized, but the collection of improbabilities, considered together, suggests that our default assumption may be incorrect." He listed the anomalies systematically. Trajectory alignment, planetary encounters, chemical composition, polarization, thermal profile, non-gravitational acceleration, jet structure, light curve irregularities. "At what point," he asked, do we consider alternatives?" The paper was met with immediate criticism. Dr. Mitchell at Caltech responded within hours. Dr. Loeb continues to interpret uncommon but natural phenomena as evidence for artificiality. This approach is unscientific. Extraordinary claims require extraordinary evidence, and speculative interpretations of anomalies do not meet that standard. The academic battle raged. Preprints, counter-preprints, comments, rebuttals. In the private email chain, the scientists watched the public debate with mixed feelings. "He's saying what we're all thinking," Dr. Santos wrote. "But is he right to say it?" Dr. Torres replied. "We don't have proof. We have anomalies. That's not the same thing." "When do anomalies become proof?" Dr. Whitfield asked. No one answered. The silence stretched. But amid the noise, the object kept moving. 3I Atlas didn't care about human debates. It follows its path, governed by gravity and whatever forces had set it in motion billions of years ago. It is now 1.62 astronomical units from the Sun, moving away at 64 kilometers per second. The jets are still active, though some observers report they may be diminishing slightly in intensity. The coma remains massive. The tail stretches millions of kilometers behind the comet, and December 19th is approaching. On that date, the comet will make its closest approach to Earth, still 270 million kilometers away. Far too distant to pose any danger, but close enough for the best observations possible. Every major telescope will be watching. Hubble, JWST, the Very Large Telescope, Keck, Gemini. Ground-based and space-based instruments all focused on a single point of light. What will they see? A comet behaving as comets do? Or something else? The sky holds its secrets, and Three-Eye Atlas isn't talking. Not yet. Every scientific revolution begins with a crack, a fracture in the accepted understanding, a data point that refuses to fit. Before Einstein, the orbit of Mercury wobbled in ways that Newtonian physics couldn't explain. Before Darwin, fossils showed creatures that had no living counterparts. Before Galileo, the moons of Jupiter moved in ways that contradicted Earth-centered cosmology. The crack is always small at first, easy to dismiss, noise in the data, an instrument error, a misinterpretation. But sometimes the crack is real, and when it's real, it widens. By mid-November 2025, the scientific community is staring at a crack. The debate over Three-Eye Atlas has split the astronomical world into two camps, not neatly, not evenly, but definitively. The majority holds firm to the natural explanation. Three-Eye Atlas is a comet. An interstellar comet, yes. Strange, yes. But a comet nonetheless. A ball of ice and rock that had formed around another star, been ejected into interstellar space, and is now passing through our solar system. This is the safe position. The respectable position. The position that requires no extraordinary assumptions. Dr. Martin Nishida at the Space Telescope Science Institute summarized this view in an interview with Science magazine. We're seeing a genuinely alien object for the first time. It makes sense that it would be different from solar system comets. It formed under different conditions. It's been traveling through interstellar space for billions of years. Of course it's strange. That's what we should expect. His logic was sound. The universe is diverse. Not every star system is like ours. Not every comet is like Halley or Hale-Bopp. Expecting uniformity is the real assumption. But the minority camp isn't going away, and their ranks are slowly, quietly growing. Dr. Loeb remains their most prominent voice, but he is no longer alone. Dr. Harold Green, a retired astrophysicist from Cornell, published a statistical analysis of the anomalies. His paper calculated the combined probability of all the observed oddities occurring together in a natural object. The number was startling, less than 1 in a million. This doesn't prove artificiality, Dr. Green was careful to note, but it does suggest that we're dealing with something extraordinarily rare, so rare that we must consider all possibilities. The paper was criticized immediately. Dr. Mitchell at Caltech called it a misapplication of probability theory. She argued that you couldn't multiply independent probabilities to draw conclusions about a single object. The approach was flawed. Dr. Green responded that the criticism missed the point. I'm not claiming mathematical proof. I'm highlighting that the concentration of improbabilities is remarkable and worth investigating seriously. The debate rages in academic journals, online forums, and conference halls. Emotions run high. Careers are at stake. Reputations are on the line, and in the middle of it all, the object keeps moving. On November 15th, the European Southern Observatory will release a new set of images from the Very Large Telescope in Chile. These will be the sharpest ground-based images yet, taken with adaptive optics that corrected for atmospheric distortion. The images are expected to show the coma in stunning detail. The jets will be clearly visible, 5 distinct streams of material radiating from the central brightness. The tail will stretch behind the object like a cosmic banner, divided into those strange parallel bands that Dr. Santos had noted earlier. But there will be something else. In the processed images, a faint structure will be visible within the coma. A barely perceptible gradient in brightness that will suggest the nucleus has an elongated shape, not spherical, not round, but stretched. The team will estimate an axis ratio of 3.1 or possibly 4.1. The nucleus will be cigar-shaped, or perhaps more accurately, it will be disc-shaped seen edge-on. This isn't entirely unusual. Many asteroids and comet nuclei have irregular shapes. They're not perfect spheres. Gravity is too weak on these small bodies to pull them into round configurations. But the elongation will add to the list of unusual features. Combined with the thermal uniformity, the chemical oddities, the trajectory alignment, and the behavior anomalies, it will be another piece of a puzzle that doesn't quite assemble. Dr. Yoshiko Tanaka at the University of Tokyo will run simulations on the shape. She will try to model how a nucleus with that elongation will behave as it rotates and outgasses. The results will be confusing. If the nucleus is spinning about its long axis, like a football spiraling through the air, the jets should exhibit certain patterns, but the observed jets won't match those patterns. If the nucleus is tumbling, rotating about multiple axes chaotically, the jets should be even more irregular than observed. They aren't. The actual jet behavior will fall somewhere between these models, as if the rotation is controlled, stabilized somehow. Dr. Tanaka won't publish her findings. They will be too preliminary, too speculative, but she will share them with colleagues privately. It's like it's too stable, she will write in an email to Dr. Torres at MIT. The behavior is too regular for a tumbling body and too irregular for a simple spinner. I don't have an explanation. Dr. Torres, who is still wrestling with the thermal uniformity data, will reply with her own observation. I'm seeing the same thing with the temperature. It's too uniform, as if something is smoothing out the gradients. They will agree to collaborate, but keep their work quiet until they have more data. November 16th will bring another development. Amateur astronomers have been tracking 3I Atlas enthusiastically since its discovery. The comet is now bright enough for serious backyard observers to capture with high-quality equipment. Online communities are buzzing with activity as hobbyists share images and measurements. One such amateur, a retired engineer named David Chen in Arizona, has been measuring the comet's brightness every clear night since early October. He is meticulous, calibrating his photometry against standard stars, accounting for atmospheric effects, and maintaining consistent methodology. When he plotted his data, he noticed something odd. The comet's brightness wasn't declining smoothly as it moved away from the sun. There were bumps, brief increases lasting a few hours, followed by returns to the baseline decline. He posted his findings on an online forum, expecting others to either confirm or refute his observations. Several did confirm. Multiple amateur astronomers reported similar bumps. Brief spikes in brightness occurring roughly every 24-48 hours. What caused them? The professionals took notice. Dr. Linda Foster at the Lowell Observatory analyzed the amateur data alongside professional observations. The bumps were real. The comet's brightness was fluctuating in a quasi-periodic manner. One explanation was jet activity. As different vents on the rotating nucleus became active, they released more material, temporarily brightening the coma. This was plausible, but the timing of the bumps didn't correlate perfectly with the expected rotation. The peaks were almost periodic, but not quite. There was drift, variation. Dr. Foster noted the phenomenon in her observation log, but will not publicize it. She will need more data, more time, but she cannot shake the feeling that the object is behaving deliberately, testing them, probing their reactions. She dismissed the thought as anthropomorphism, projecting intent onto a mindless rock, but it lingers. November 17th, 3 days from now. The tension is building, the observations are accumulating, the anomalies are mounting, and the December 19th approach is now just 1 month away. In the quiet of observatories around the world, scientists are preparing. Telescope time has been allocated, instruments are being calibrated, observation plans are being finalized. This will be humanity's best chance to study 3I Atlas. After December, the object will fade rapidly. It will be moving away from both the sun and Earth, dimming as the solar radiation weakens and distance increases. If there are answers to be found, December will be the month to find them. But what if the answers are not what anyone expected? Dr. Torres, sitting in her office at MIT, is staring at her computer screen. The thermal data is still there. The impossibly uniform temperature map. The lack of gradients that physics demanded. She has run out of natural explanations. Every model failed. Every hypothesis fell short. In a moment of frustration, she typed a new search query into her database. Not for comets, not for asteroids, but for artificial structures, spacecraft, probes, satellites. What thermal signatures did human-made objects show? She felt foolish even asking. But she was out of options. The results came up. Heat pipes, thermal louvers, active cooling systems, technologies designed to maintain temperature uniformity across a structure. The thermal profiles were similar. Not identical, but closer to what 3I Atlas was showing than any natural body. She closed the browser, deleted her search history, leaned back in her chair. Outside her window, the November evening is fading into night. Stars are emerging. Somewhere among them, invisible to the naked eye, 3I Atlas is continuing its journey. 4.6 billion years old. Older than the sun. A relic from the early galaxy. Or was it? The age estimate came from assumptions about its origin. If it had formed in a different star system and traveled through interstellar space, it had to be old. Billions of years old. But what if those assumptions were wrong? What if it hadn't been drifting aimlessly for eons? What if it had been sent? The thought was terrifying, exhilarating, impossible. Dr. Torres shook her head. She is a scientist. She deals in evidence, not speculation. But the evidence is pointing somewhere uncomfortable. The divide in the scientific community is deepening. The majority still holds firm. But cracks are forming. Doubts are creeping in. And somewhere out there, beyond human sight, but not beyond human reach, the object keeps moving. Watching, observing, indifferent. No one knows. But everyone is starting to wonder. November 18th will bring new observations from the Hubble Space Telescope. The goal will be to image the nucleus directly, separating its light from the surrounding coma. What it will see is unexpected. The central brightness won't be single, it will be double. 2 points of light separated by approximately 200 kilometers, orbiting each other within the coma. 3I Atlas will be revealed to be binary. This will be significant. Some asteroids and comets are known to be binary systems, two bodies orbiting their common center of mass. It's natural. Gravity brings rocks together in space, but the discovery will change everything. If 3I Atlas is binary, all the models will need revision. The jets, the thermal profile, the rotation, the mass, everything will have to be recalculated. Dr. Robert Kim at the Space Telescope Science Institute will lead the analysis. He and his team will work around the clock, processing the Hubble data and running new simulations. Their preliminary findings will be startling. The two components will be roughly equal in size, each about 2.5 to 3 kilometers in diameter. They will be orbiting each other with a period of approximately 14 hours. The orbit will be nearly circular and stable. This will explain some things. The complex light curve will make sense now. Two bodies rotating and orbiting will create overlapping signals. The thermal uniformity could be partially explained by mutual heating as the bodies tidally interacted. But it will raise new questions too. Binary. Comets from our solar system are rare. To find an interstellar binary will be remarkable. The probability calculations will need updating, and there will be something else. The orbit will be too stable, too circular. When two bodies orbit closely, tidal forces should cause eccentricity. The orbit should be slightly elongated. Over millions of years, the orbits might circularize, but for a system that had been traveling through interstellar space, experiencing gravitational perturbations from passing stars and the galactic environment, the orbit should show some distortion. It won't. The orbit will be almost perfectly circular. Within measurement error. Dr. Kim won't know what to make of it. He will consult with colleagues. They will be puzzled too. Binary systems can have circular orbits, Dr. Green will note when Dr. Kim shares the data. But maintaining that circularity over billions of years of interstellar drift is unlikely. Unlikely but possible, Dr. Kim will reply. Yes, Dr. Green will agree, like everything else about this object. The discovery of the binary nature will be released to the public on November 20th. The news will explode. Interstellar comet is actually two objects, headlines will proclaim. The amateur astronomers will verify the finding within days. With the right image processing, the double nature will be visible even in ground-based observations. 3I Atlas will have revealed another layer of its mystery. And as November enters its final weeks, the anticipation for December 19th will intensify. Telescope time is being jealously guarded. Every major observatory has 3I Atlas on its schedule. The competition for observation slots is fierce. Dr. Foster at the Lowell Observatory has secured 12 hours of telescope time spread over the week around closest approach. She is planning a comprehensive study. Photometry, spectroscopy, polarimetry, imaging. Dr. Anderson in the Canary Islands has similar plans. Her polarimetry will track any changes in the surface properties as the object recedes. Dr. Chen at Keck is prepared to continue her chemical monitoring. Will the nickel-iron ratio finally stabilize? Will new elements appear? Dr. Torres at MIT is coordinating with JWST for additional thermal mapping. The new binary model needs testing. Everyone is preparing, and everyone is quietly wondering the same thing. What will December reveal? November 24th will bring an unexpected development. The European Space Agency will announce that their JUICE mission, currently en route to Jupiter, will conduct observations of 3I Atlas during its close approach. The spacecraft is still far from its destination, but its instruments are operational and capable of detecting the comet. JUICE carries a camera, spectrometers, and particle sensors. It will observe from a vantage point impossible for Earth-based telescopes, providing data from a different angle. But there will be a catch. JUICE's primary antenna is pointed toward Earth, for Asu Dedao. Communication. Reorienting the spacecraft to observe 3I Atlas will disrupt data transmission. ESA is negotiating the trade-offs. The observation is scheduled tentatively for late November through early December. The data will take time to arrive, perhaps not until early 2026. Still, the knowledge that another observer is out there, millions of kilometers away, will add to the sense of collective human effort. We are all watching. Together. November 26th, Thanksgiving in the United States. Dr. Torres will sit at her family's dinner table, surrounded by relatives discussing politics, weather, and football. Normal topics, comfortable topics. But her mind will be elsewhere. She has been wrestling with the thermal data for weeks. The binary discovery has helped somewhat. Mutual tidal heating can account for some of the uniformity, but not all of it. The numbers still don't add up. And now she will have another puzzle. She has been reviewing the jet patterns, trying to understand which body is producing which jets. The 5 jets should correspond to specific vents on the surfaces of the two components. By tracking the jets over time and correlating them with the orbital motion of the binaries, she will be able to map the active regions. The mapping isn't working. The jets do not correlate with either body's rotation. They seem to fire independently, as if controlled by something other than solar heating and geometric exposure. At the dinner table, her uncle will ask if she's okay. She seems distracted. "Just work stuff," she will say. "This comet I'm studying." "The alien one?" her teenage nephew will ask, grinning. "It's not alien," she will say automatically. "It's just from another star." "Same thing," the nephew will laugh. Dr. Torres will smile but won't respond. She isn't sure he is wrong. November 28th. 4 days before December. Dr. Harold Green, the retired astrophysicist who'd published the probability analysis, will release a new paper. This one will be different. He has been collaborating with Dr. Marcus Lee, a computer scientist specializing in signal processing. Together, they have analyzed the light curve data looking for patterns. They will find one. Buried in the brightness fluctuations will be a faint but regular signal. A modulation at a frequency of 0.021 Hz. That corresponds to a period of 47.6 seconds. Almost exactly the period that Dr. Whitfield at Arecibo had detected in the radio signal. The one that appeared briefly on November 13th and then vanished. The match will be too close to be coincidental. Dr. Green won't draw conclusions in his paper. He will simply note the correlation and call for further observation. But the implication will be clear. If the same period is appearing in both optical and radio data, something is producing it. And that something is either a remarkable natural phenomenon or an artificial signal. The paper will go viral within hours of posting. The divide in the scientific community will crack. Wider. On one side, researchers will insist the pattern is coincidental or the result of analysis artifacts. They will point out that periodicities can be found in random data if you look hard enough. The human brain is wired to see patterns. On the other side, researchers will note that independent detection of the same period in different wavelengths is significant. It warrants investigation. The debate will be no longer quiet. It will be loud, public, contentious. And through it all, 3i Atlas keeps moving. By the end of November, it will be 1.75 astronomical units from the Sun, still approaching Earth, which is orbiting at 1 AU. The closing distance means the object will appear brighter in Earth's sky, despite moving away from the solar heat source. The coma is still massive, the jets are still active, the binary dance will continue within the shroud of gas and dust, and December 19th is now less than 3 weeks away. In the quiet moments when the telescopes are processing data and the scientists are reviewing results, a strange feeling will settle over those who are paying close attention. A feeling that they are being watched back. That the object isn't just a passive traveler. That it is aware. Present, engaged. This is anthropomorphism. Wishful thinking. Unscientific. But the feeling will persist. 3i Atlas was 4.6 billion years old. Supposedly. A remnant from the ancient galaxy. But its trajectory says otherwise. And as November gives way to December, as the object draws closer to Earth and the data intensifies, the awakening will continue. Not just of the public to the mystery, but of the realization that the universe might not be as empty as we'd thought, that among the stars and the vast darkness between worlds, something is moving. Something old, something deliberate, something that had chosen to pass through. Or will it have chosen to arrive? Some questions have answers, others have only echoes. In the first week of December 2025, the world will watch as 3i Atlas draws closer to Earth. Not physically dangerous, 270 million kilometers is a vast distance, but psychologically close. Close enough to feel intimate, close enough to wonder. The December observations will begin. Every major telescope on Earth and in space will be pointed toward that single point of light in the constellation Virgo. The data will flow like a river, terabytes of information cascading into servers around the world. And the anomalies will persist. The binary system will continue its stable orbit. 14 hours. Circular, unchanging. The jets will pulse in their patterns, not quite matching any model. The temperature will remain uniform across both bodies. The polarization will hold steady. The chemical signature will stay exotic. Nickel without iron. Then iron appearing. Then vanishing again. And faintly, barely detectable, that 47-second periodicity will continue to appear in the data. In the light curves. In the radio silence. In the spacing of the brightness. Bumps, like a heartbeat. On December 10th, Dr. Torres will finally submit her paper on the thermal anomalies. She will have revised it countless times, trying to find language that is honest without being sensational. The thermal behavior of 3i Atlas will remain inconsistent with natural models, she will write. While the binary nature of the system introduces complexities, the degree of thermal uniformity observed exceeds what tidal heating and mutual radiation can produce. An unknown mechanism is at work. She will stop short of suggesting what that mechanism might be. The paper will be accepted for expedited review. On December 12th, Dr. Green and Dr. Lee will publish their follow-up on the periodicity. More data will have confirmed the pattern. The 47-second signal will be present across multiple nights of observation, fading in and out but recurring. The signal's persistence across wavelengths and time suggests a physical origin, they will conclude. Whether this represents a natural rotational modulation or an artificial transmission requires further study. They will be careful, cautious, but the word transmission will be there, in print, in a peer-reviewed journal. The mainstream scientific community will push back hard. Dr. Mitchell will organize a consortium of 23 prominent astrophysicists who will co-sign a letter to the editor. The enthusiasm surrounding 3I Atlas will unfortunately generate speculation that outpaces evidence, they will write. While the object is undoubtedly unusual, all observed features will remain within the bounds of natural phenomena. Claims of artificial signatures will be premature and scientifically unjustified. The letter will be influential. It will represent the voice of the establishment, the weight of authority. But the doubts will have taken root. December 19th will arrive. The closest approach. The moment of maximum revelation. Or so everyone will hope. On that night, telescopes around the world will be active. The Very Large Telescope in Chile will capture the sharpest images yet. The binary components will be clearly resolved, two distinct points of light separated by 200 kilometers, dancing in their stable embrace. The JWST will conduct infrared spectroscopy, analyzing the thermal emissions in unprecedented detail. The data will show the temperature uniformity is real, confirmed at higher resolution than ever before. Hubble will image the jets, tracking their morphology over hours as the binary rotates and orbits. The patterns will be complex, beautiful, and unexplainable. Ground-based observatories will measure the polarization, the chemical emissions, the brightness variations. Everything will be recorded, cataloged, preserved, and the 47-second periodicity will be there. Faint but persistent. A signal buried in the noise, barely above the detection threshold, but present. The data will be overwhelming. It will take months, perhaps years, to fully analyze. But on that night, as the scientists gather their observations, a quiet realization will settle over them. They are not going to solve this mystery. Not now. Not with the data they have. The object will be too far away for detailed study. Even at closest approach, 270 million kilometers is an enormous distance. They won't be able to sample it, won't be able to touch it, won't be able to probe its interior. They will only be able to watch, measure, infer, and their inferences will be incomplete. By late December, the object will be fading. Moving away from both the sun and Earth, its brightness will diminish day by day. The jets will be weakening. The coma will be shrinking. The spectacle will be ending. In the final days of December 2025, as the world celebrates holidays and marks the passage of another year, 3I Atlas will begin its slow disappearance. It will pass by Jupiter in March of 2026, but that encounter will be beyond our primary focus here in 2025. What mattered will be what we'd learned, and what we hadn't. We'd learned that interstellar visitors exist, that they're diverse, that they carry the chemical signatures of distant worlds. We'd learned that our assumptions about the universe are incomplete, that objects from other stars don't follow the same patterns as objects from our system. We learned that the cosmos is full of surprises. But what won't we have learned? We won't have learned what 3I Atlas truly was. Natural or artificial, ancient traveler or deliberate visitor, random wanderer or purposeful probe. The data will have pointed in multiple directions. The anomalies could be explained naturally with enough creativity and flexibility, but those explanations will have required stretching models beyond their usual bounds, invoking conditions not seen elsewhere, assuming coincidences that strained probability. Alternatively, the anomalies could be evidence of something else, something designed, something intelligent. That explanation will be simpler in some ways. A single assumption, artificial origin, could explain the trajectory alignment, the chemical oddities, the thermal regulation, the periodic signal, the stable binary orbit, the controlled jets. One assumption versus a dozen. But that one assumption will be enormous, world-changing, paradigm-shattering. And so the debate will continue. In the final analysis, 3I Atlas will leave us with something more valuable than answers. It will leave us with wonder. The realization that the universe is vast beyond comprehension, that we are small within it, that our knowledge is limited, that out there among the stars, things exist that we don't understand. Can't understand. Not yet. And that's okay. Because the not knowing is what drives us forward. The mystery is what keeps us looking up. The questions are what make us human. As December 2025 draws to a close, as the object fades from our instruments and our immediate attention, a strange peace will settle over those who'd spent months obsessing over it. They'd done their best. They'd gathered the data. They'd run the models. They'd debated the interpretations. And they'd confronted the limits of their understanding. Some will be frustrated. They wanted answers, certainty, closure. Others will be humbled. They will recognize that the universe doesn't owe us explanations. It simply is, in all its complexity, all its mystery, all its grandeur. Dr. Torres, sitting in her office on December 31st, will stare at her computer screen. The thermal data will still be there. Unexplained, inexplicable. She will have spent months trying to understand it, and she will have failed. But in that failure, she will have found something else, a sense of perspective, a reminder that science isn't about having all the answers, it's about asking better questions. And 3i Atlas will have given her a question worth asking. What else is out there? She won't have an answer, but she will have a lifetime to search. And that will be enough. Outside her window, the night sky will be clear. Stars will burn against the blackness, each one a sun, each one potentially host to worlds, to objects, to mysteries. Somewhere among them, fading into the cosmic distance, 3i Atlas will continue its journey. Where will it have come from? Where is it going? What is it? We won't know. We might never know. But we'd seen it, measured it, wondered at it. And in that wondering, we'd touched something profound. The truth we carry forward is not the truth about 3i Atlas. It's the truth about ourselves. That we are curious, that we are humble, that we are small, and that we are part of something immense, something ancient, something ongoing. The object fades, the stars remain, and we continue to wonder, as we should, as we must, as we will, forever.